Hello dear viewers, welcome to TV Math Hub. This is your home for clear and practical mathematics. In our today's session, I will be taking you through objective questions for linear algebra. For those at the university level and are preparing for their final examinations in linear algebra, please I get you sorted within this video. So make sure you watch up to the end. We shall look at 60 objective questions, and you will be given 30 seconds for each of the questions to think about the correct answer. Then after that, we shall look at the correct answer together, and make sure you do this for all the questions, and at the end of it all, we shall compile all the marks that we have obtained from the 60 questions, and we shall present this in the comment section. So please don't forget to like, to share, and also comment on this video. So let us get started. We shall look at question number 1. So here is question number 1. So please take 30 seconds to answer this question. So let us look at the answer. So we are given that if A and B are square matrices of the same order, then trace of AB is equal to, so the required answer here is part C. So trace of AB is same as a trace of BA. So the answer here is a C. So that is the required answer. So next we shall look at question number 2. So let us look at question number 2. So here is question number 2. Get the answer for question number 2 within the 30 seconds. So let us look at the required answer. We are told that if A and B are square matrices of the same order, if A and B are square matrices of the same order, then what is AB transpose? So what is AB transpose? So AB transpose is same as B transpose A transpose. So that is B. So when you take the transpose of the product, AB is same as getting B transpose times A transpose, not A transpose, B transpose. That will be wrong. So it means this B will be the required answer. Okay, so let us look at the next question, and that will be question number 3. Let us look at question number 3. So here we have question number 3. And you have 30 seconds to answer that. Okay, so for question number 3, they are saying for all square matrices A and B, is it true that determinant of A plus B is same as determinant of A plus determinant of B? So what is the answer that you have obtained there? So this is not true. This is not true. So this is false. The reason is the determinant function is not linear with respect to matrix addition. while determinant of A plus B in some cases can be same as determinant of A plus determinant of B, but this does not happen in all other cases. In some cases, this can be true, but in many cases, this cannot happen. You can consider any, we can consider any of the examples. For example, if you have A as, for example, 1, 0, 0, 0, you have B as, for example, 0, 0, 0, 1. So let us look at this matrix. If you get A plus B, this will be same as 1, 0, 0, 1. This will be the matrix. That is matrix AB. So what will be the determinant of A plus B? The determinant of A plus B will be same as getting this product, that is 1 minus 0, which is 1. And what will be the determinant of A? Determinant of A here, the determinant of this is 0. What is the determinant of B? The determinant of B here is also 0. So what will be determinant of A plus determinant of B? Determinant of A plus determinant of B will actually be 0. So you realize here you got your determinant as 1, but the determinant of A plus determinant of B here is 0. So 1 cannot be equal to 0. So clearly we can see that this one here cannot always be true for all the matrices you pick of A and B. So that means that for all square matrices A and B, it is not true that the determinant of A plus B is equal to determinant of A plus determinant of B. So that answer there will be false. So that is for that question. So we shall look at the next question. So here we have our next question. So we have a linear system said to be consistent if it has. So we have our different options, and please you have 30 seconds to think about the answer. Okay, so time is over. So we look at the answer. We are told a linear system is said to be consistent if it has. So here the required answer. So we are given the option infinite remaining solutions, no solution, at least one solution, none of the above. So the answer is C. A linear system is said to be consistent if it has at least one solution. First of all, it is consistent if it has a unique solution. Remember, we have three types of solutions. We have a unique solution, we have infinite remaining solutions, and another one we have no solution. So a system is said to be consistent, first of all, if it has a unique solution and if it has infinitely many solutions. So for that case, the required answer here would be at least one solution, because at least one solution combines unique solution and infinitely many solutions. So for that case, if you say only infinitely many solutions, you will have left out this. If you have no solution, then the system is inconsistent. If there is no solution, and if there is at least one solution, meaning there can be one solution or many solutions. And that would be the case for unique solution and infinitely many solutions. So there it means the required answer here would be at least one solution. So that's all about this. So we look at the next question. So in our next solution question, we are given which of the following matrices is in reduced row echelon form. And here are the options. Here are the options. So let us look at the answer for that case. Think about the answer within the 30 seconds first. Then we look at the required answer. Okay, so the time is up. Let us look at the solution. Here the solution is A. The reason is for the matrix to be in a reduced row echelon form, then there must be leading ones and they should be following this order here. So we have 1 here. Then all the entries where we have a leading 1 must be 0. All other entries other than the leading value must be zeros. So we can see we have zeros here. Here we have a leading 1 in this row here, which leading 1 is here. So moving from left to the right, moving from left to the right, and all other entries in that column where we have a leading 1 are zeros, like this one and this. Then when we come to this row, you realize we have also a leading 1, and this leading 1 in this column here where we have a leading 1, all other entries are zeros. So all these other entries here are zeros, and for that case, it means this matrix here qualifies to be a reduced row echelon form. When you look at this matrix here, you realize a leading 1 is there, which is true. All other entries within this are zeros, so this one is okay. Then when you come to this one here, that is the second row, you have a leading 1, but you realize that in this column not all other entries are zeros because you have a 1 here, so that disqualifies it. So this will be disqualified. So this one is not in reduced row echelon form. When we come to this, let us look at the leading 1 is there, but when you look at in other entries within that column, you have a non-zero, which is here. So this one will automatically be disqualified. So if there is a leading 1, all other entries must be zeros. So similarly, when you look at this, the leading 1 is there, but not all other entries are zeros. So you realize this is a 0, but this is not. Okay, so this one will be disqualified. When you look at this, you realize a leading 1 is there, all other entries are zeros in this column, which is okay. When you come to this matrix here, you don't have a leading 1. So, and again, for it to qualify to be a row echelon, or the row that is consisting of zeros must be lying at the last bottom, must be the last row, meaning that this must have come in the last, should have been the last row here. But if it comes within the middle or the first one, then it becomes disqualified. The row of zeros must appear at the bottom. So for that case, this one here is appearing in between. So this will be disqualified as well, because a row of zeros is appearing in between other rows, and yet it must be at the bottom. So for that case, we shall have our part A as the answer for this question. So we shall look at the next question. So you have 30 seconds. So time is up. Let us look at the solution. We are told that which of the following condition is incorrect for matrix multiplication. So this one here, if you multiply A with BC, it will be same as multiplying AB first. Then you do this. This is okay. So A into B plus C is same as multiplying A with B, A with C. This is also true. Then AB is equal to 0 if either A or B is 0. That is true. If A is 0, if A is a 0 matrix, and B is not a 0 matrix, and then if you get AB, the product will give you a 0, which is true. Likewise, if B is 0 and A is not a 0 matrix, when you get AB will give you a 0. You can prove that. You can let any, you have A, 1, 2, 3, 4, then you have B, which is a 0 matrix. Then multiply these and see what you will get. Automatically, AB should be equal to 0. So if you also do the vice versa, that is if B is not If B is taking up this one maybe and A is taking a zero matrix, you should be able to get a zero matrix. So it means this is also true. Then we are looking for the condition which is incorrect for matrix multiplication, and this one here is not correct because AB is not equal to BA. Because matrix multiplication is not commutative in general, though it holds for some specific cases. So this will be the condition which is incorrect. So answer will be D, because AB is not equal to BA for general cases. Though it can be true for some specific cases, but generally this is always not true because matrix multiplication is not commutative. So that will be answered, and we shall look at the next question. And I hope you are noting down your answers for each of the questions. So we need to look at the next question. And please, if you are here and you haven't subscribed to this channel, please kindly do so. First hit in the subscribe button, and that's all. You will always get notified whenever a new video is uploaded. It is completely free of charge. Simply hit in the subscribe button. Don't forget to like and share this video. So let us look at the next question. Your time starts now. So time is up. Let us look at the answer. So we are told a matrix A, which is equal to having elements Aij of order m by n, is a square matrix if m is equal to n. A square matrix is a matrix that has got an equal number of rows and columns. It has equal number of rows and columns. So for rows and columns here to be the same, what should happen? It means if it is m by n matrix, then it means m must be equal to n, such that you either have m by m or else you have n by n. This will now qualify to be a square matrix. So it must have equal number of rows and columns, and for that case m must be equal to n, and this will be our answer. This will be not true, this will not be true, this will not be true. So that is all about this question. So we look at the next question. So your time starts now. Your time is up. Let us look at the solution. We are told that a matrix A, which is m by n matrix, is a row matrix if, first of all, what is a row matrix? A row matrix is a matrix that has got exactly one row. Exactly one row. A row matrix is a matrix that has exactly one row, meaning that it can be 1 by 2, it can be 1 by 3, it can be 1 by 5, it can be 1 by 10, but it must have only one row. Remember, this represents rows, this represents the number of columns. So if it is to have only one row, then what should happen to this matrix? So if you have m by n matrix and you need it to have only one row, then it means m must be equal to 1. And if m is equal to 1, then you will have a 1 by n matrix. So this matrix A is a row matrix if m is equal to 1. If m is equal to 1, then you will have a 1 by n matrix, which is a row matrix. So this matrix here is a row matrix if m is equal to 1. So if m is equal to 1, and this becomes our answer. So C is the answer for this question. We look at the next question. So here is our next question, and you have only 30 seconds to get the answer. So your time is up. Let us look at the answer. So we are told that in a square matrix A, which is equal to Aij, this is an n by n matrix. The elements A11, A22 up to ANN are called dash elements. So think about this matrix, a 2 by 2 matrix, having A11, A12, A21, A22. This is n by n matrix, but let us deal with a 2 by 2 matrix. So these elements here, A11, A22, are called A11, A22. These elements here form what we call a diagonal. So this is the main or leading diagonal. So these are what we call the diagonal elements. In other words, these elements here, A11, A22, A33, up to ANN, are what we call diagonal elements, not scalar, not identity, and not unity. So the answer for this question will be A, where we have diagonal elements, and that will be answered. Then we shall look at the next question. So looking at the next question, you have 30 seconds. Your time is up. We look at the required answer. So we are told the square matrix A, which is m by n matrix, is called upper. This is a square matrix, so correct that. This should be n by n matrix. So a square matrix A, which is n by n matrix, is called upper triangular if A of ij is equal to 0 for all. Okay, so let us look at the required answer here. First of all, we are talking about a square matrix. So a square matrix, we can think about a square matrix for a 2 by 2, maybe A11, A12, let us look at a 3 by 3, A13. So A21, A22, A23, and lastly we shall have A31, A32, and A33. So we shall have that. So we shall say that this matrix here is upper triangular, if Aij is equal to 0 for all. Now, for it to be called upper triangular, then all entries below the main diagonal must be equal to 0. So this is our main diagonal. So the entries below this main diagonal, we have this, and we have that. So these entries must be zeros. So when these ones are zeros, it means we shall have an upper triangular matrix, and that is the matrix A11, A12, A13, A0, A22, A23, 0, 0, A33. So this matrix here, where these entries here below the main diagonal are all zeros, is what we call an upper triangular matrix. So they are asking, a square matrix A, which is an n by n matrix, is called the upper triangular if Aij is equal to 0 for all. So where do we have the entries where the entries are equal to 0? This is at this given point. at this given point and at this given point. So 1, we have I is greater than j, so we are having aij equal to 0 here, a21 is equal to 0, a21 is equal to 0, a31 is equal to 0, and a32 is equal to 0. So there is a relationship between these elements which are equal to 0, especially in regards to ij. This is ij, and this is also I and j. So meaning your I here is 2, your j is 1. Your I here is 3, your j is 1. Your I here is 3, your j is 2. So you realize in all the cases, I is greater than j. In all the cases, I is greater than j. And for that case, it means the square matrix is called upper triangular if aij is equal to 0, and that happens for all the entries where I is greater than j. So for that case, it means our answer will be part A. So our answer will be I is greater than j for upper triangular. So you need to also think about lower triangular matrix. So lower triangular matrix. So what happens for lower triangular matrix? All the entries above the main diagonal are zeros. This one, and this, and all of them have something in common. You realize this represents I, this represents j, I represents j, this I, this j. So you realize in all the cases, in all these cases that we are having here for lower triangular matrix, then j is greater than I. In all the cases, j is greater than I, because 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. So in all cases, j is greater than I, or I is less than j. So this would be the condition that would be satisfied for all ij equaling to 0. For all ij equaling to 0, then j must be greater than I. So that is for the case of lower triangular, and that is when the question now is specifically talking about lower triangular matrices. So we shall look at the next question. So you have 30 seconds to have this one answered. So time is up. Then we shall look at the solution. We are told a matrix all of whose elements are 0 expecting the main diagonal is called a 1 unit matrix. For unit matrix is a specific matrix where the entries in the main diagonal are 1s and all other entries are 0s. This is a specific matrix, specific diagonal matrix. This is a specific diagonal matrix. So we have seen a unit matrix is a specific diagonal matrix where the entries in the diagonal are equal to 0. However, unit matrix is same as an identity matrix. So this is still the same identity matrix. Then when we talk about scalar, a scalar is actually when you are having a scalar like 2 multiplied into a matrix. Then we talk about diagonal. So a diagonal matrix is a square matrix where all of diagonal elements are zeros, meaning that when you have like a 0 0 p, these elements here, the elements of the main diagonal, we have this and this are all zeros, but the elements in the main diagonal can be any values. So meaning that if you have a 6, a 0 0, a -1, this is a diagonal matrix, so long as in the of the main diagonal all other elements are zeros. So when you talk about a 3 by 3 diagonal matrix, you can have even 7, 0 0, 0 0 0, 0 0 0. This is also a diagonal matrix. You realize elements of the main diagonal, these ones here are all zeros. So if it happens and maybe one of them is not a 0. For example, you have 7 as 0, 0, but 1 is here. So there is a 1 here. Then this one here is not a diagonal matrix. For it to qualify to be a diagonal matrix, elements of the main diagonal, elements that are not within this diagonal here, have to be equal to 0. So these ones are zeros, but this element here is not a 0. So for that case, then it means this will not be a diagonal matrix. So let us look at the required answer. So the required answer for this case, will be a diagonal matrix. So a diagonal matrix is a matrix where the elements of the main diagonal are zeros. So that is the required answer. So we look at the next question. So you have 30 seconds to think about the answer. So time is up. We look at the solution. So basically, we have already defined what a diagonal matrix is. We say the diagonal matrix for all any matrix should qualify to be a diagonal matrix if only the off-diagonal elements are zeros, meaning the elements that are not within the main diagonal must be zeros. So when we look at this one here, you look at these elements that are off the main diagonal, elements which are not in this diagonal. So that's why we are first removing this diagonal, then we look at these elements. So these elements must be zeros. These elements must be zeros. So when you look at these elements, you realize this is not a 0, this is not a 0, so this will be disqualified. B, when you look at the main diagonal is this. No matter what is in the main diagonal, it does not, all these ones can also be any values, but these others which are off the main diagonal must be zeros. So these are all zeros, which is okay. This is a 0, which is okay, but this is not a 0, this is not a 0. So this will be out. When you look at this, we first fence out this. When we fence out this, we look at what is here. This is a 0, 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 this is a 0. So you realize the entries of the main diagonal are all zeros. So this one will qualify to be a diagonal matrix. No matter what is in this diagonal here, our main emphasis should be the off-diagonal elements. Elements that are not within the main diagonal. That is where the emphasis should be. And those elements should be equal to 0. So when you look at this, the elements of the main diagonal are all zeros. So this qualifies to be a diagonal matrix. No matter which value is here, what should be the main cause here is these elements which are not in this diagonal. The elements in this diagonal can take up any of elements, can be negatives, can be positives, can be zeros. So you fence out to this, then look at these other elements. Then if they are all zeros, then you conclude that it is a diagonal matrix. So C will be the answer. So we shall look at the next question. So you have 30 seconds to think about the answer. And please, whenever you get the answer, write it somewhere. At the end of this video, we shall compute the marks that you have got out of 60. We shall look at 60 objectives. So time is up. We look at the solution. We are given that A and B are matrices of orders. A is of order m by n, and P by Q respectively, and B is P by Q. So this is A, this is B. And then the product AB is possible. The product AB is possible if you are able to multiply A with B. What should happen? So A is m by n, B is P by Q. So for these two matrices to be able to be multiplied together, then something should happen. This and this must be the same. The number of columns in A must be equal to the number of rows in B. For matrix multiplication to take place, the number of columns here in this matrix must be equal to the number of rows in this matrix. In other words, you can multiply a 2 by 2 matrix with a 2 by 3 matrix, so long as this and this are the same. But you cannot multiply a 2 by 1 matrix with a 2 by 3 matrix. When this and this are not the same, the two matrices cannot be multiplied together. So what happens is, for the two matrices to be able to give us the product, to be multiplied together, then these must be the same. The number of columns here must be the same as the number of rows in this matrix. So for that case, if we are multiplying A and B, where A is M by N and B is P by Q, then N must be equal to P. Otherwise, the two matrices cannot be multiplied. So we need to look at where we have N must be equal to P. So N must be equal to P, and that is A. So N must be equal to P for the two matrices A and B to be multiplied together, and that would be the answer. We shall come to the next question. If A and B are two non-zero matrices, is it possible to have AB equaling to 0? So you have two options. One is no, another one is yes, and you have only 30 seconds. So time is up. Let us look at the answer. We are given that if A and B are two non-zero matrices, they are two non-zero matrices, and we want to establish the possibility of having AB equaling to 0. So is it possible? If it is possible, then we must be able to show this by an example. If you have, for example, matrix 1, 0, 0, 0, this is a non-zero matrix because not all the entries are equal to 0. You have another matrix B, which is, for example, 0, 0, then, for example, 1, 0. We can have 1, 0 here. If you have such a matrix, let us see if you multiply the two matrices, are you able to get a 0 matrix, AB? So AB is 1, 0, 0, 0. Then B is 0, 0, then 1, 0. So let us try to multiply this row by column. 1 times 0 is 0. This times that is 0, so we have 0. This times that is 0. This one will also give us 0. This will be 0. This will be 0. This multiplied here is 0. Multiplied here is 0. So you are able to get a 0 matrix. So A is not a 0 matrix. Is not a 0 matrix. B is not a 0 matrix. But when you get AB, you are getting a 0 matrix. So it is possible to have AB equaling to 0 even when A and B are not 0 matrices. So the answer would be yes. So that would be the required answer, and I hope you have passed that one. So we look at the next question. So in our next question, we are given which row does not hold in matrices. And you have only 30 seconds. So time is up. Let us look at the solution. So which row does not hold in matrices? A, we have associative row of multiplication. B, distributive row. So we shall look at each of these. So associative, if you have A into BC, is this one same as having AB into C? This is true. This one holds. if you have A into B plus C, that is distributive law of multiplication over addition. If you have this, is it same as having AB plus BC? This is also true. Then cancellation law, if you have, for example, AB, and this is equal maybe to BC, can we cancel this and this, and then we say A is equal to C? If you have AB is equal to AC, can you cancel this and this, and you say B is equal to C? This is not true. This cannot hold in matrices. If you get AB and you get BC, if AB is equal to BC, it does not mean that A is equal to C. So if you have AB equaling to BC, you cannot have A equaling to C. This does not hold. So in general, this does not hold. So AB equaling to AC does not imply AB equaling to AC does not imply that B is equal to C. This does not imply, if you're having this, it does not imply that B is equal to C. So this cannot hold in general, meaning that the odd man out here will be C. So C does not hold. A holds, B holds, but C does not hold. So cancellation law does not hold. So both A and B holds. So this is true. But the one which is not true is this. So C will be the required answer. So let us also look at now the next question. Let us look at the next question. So the next question is so we have the different options. So which of the following is correct? You have 30 seconds. So we have already looked at different properties that are considered when we are looking at matrices, and I hope this one is now very clear to all of us. So this one is true. This one is true for the matrices. This is also true for the matrices when K is a scalar. K into AB is same as multiplying K with A, then you multiply by B. So it means all of the above. So D will be the correct answer. So that will bring us to the next question. So you have 30 seconds to look at that question. So we are basically looking at the transpose of matrices, and we are having that A, B transpose is same as B transpose times A transpose. This is true. This is true for matrices. If you have A, B transpose is same as B transpose times A transpose. Then if you get A transpose, then you take again the transpose of A transpose, then you will come back to the same matrix A. So this is true, because transposing twice brings you back to the original matrix. Then K A transpose is same as K, because K transpose will remain, K is a scalar, so it will not be affected by the transpose. So this is also will also be true. So it means D will be the correct answer, because all the three above are correct. So that will be true for all the matrices. So that would be the answer for that given question. So we shall look at the next question. And you have 30 seconds to have that one answered. So next, let us look at the solution to this. We are told that A and B are non-singular matrices, meaning that they are invertible. Non-singular means that they are invertible, or they have got the inverse. A has an inverse, B can also have an inverse, and they are of the same order. Then we need to look at AB inverse. So what will be AB inverse? AB inverse is not equal to AB. This is not generally true. And B, we are told A inverse, B inverse. So AB inverse from properties of inverses, then we have this is true, that AB inverse is same as B inverse times A inverse. This is true. However, this is not true. Is equal to BA. This is not generally true. So it means this will be the answer. So that will be the answer for this question, that AB inverse, when you take the inverse of AB after multiplying A with B, it will be the same as someone who has got B inverse times A inverse. So that will be the required answer for that case, and I hope you have passed that one. Make sure you are putting these solutions down. Make sure that whichever question we look at, you have got the answer. Then at the end, we shall try to compute and see how many marks you have obtained in all the 60 MCQs. So we look at the next question. So here is the next question. And you have 30 seconds. So time is up. I hope you have already secured the answer for that. So we have A is invertible, meaning that A has got the inverse. Then we need to look at an AB is equal to 0. Then what will happen? So we are told that A is invertible, meaning that the inverse exists. And for that case, since we have that AB is equal to 0, we shall try to multiply A inverse on both sides. So A inverse, then times 0. This is a 0 matrix, which is 0. So this can be same as A inverse, then times A into B, which is same as if you get A inverse. Since the inverse exists, then when you get A inverse, you multiply it with a 0 matrix, you remain with a 0 matrix. A inverse times A gives us an identity matrix, then times B, which is equal to 0. But an identity matrix times B will be a B. If you get an identity matrix, you multiply it with a matrix, you remain with a B, and this would be equal to 0. So generally, it means B will be equal to 0, and the answer here will be B, where we have B as 0. This will be off, this will be off, and this will be off. So that will be the answer for this given question. So B is equal to 0 is the answer. So if A is invertible and AB is equal to 0, then B is also equal to 0. So that will be the answer. We look at the next question. So you have 30 seconds to look at the answer for that question. So I hope you have already got the answer. Let us try to look at the answer for this question. So from here, we can easily solve this by first of all putting it in the system of equations. So we shall multiply this out. So we shall have negative 3 times x1, that is negative 3x1, plus 3x2, which is equal to 0. Next, we shall have 1 times x1, that is x1, and this is minus x2, which is also equal to 0. So I want to get the values of x1 and x2. So I will multiply here by 3, and this will give us negative 3x1 plus 3x2 is equal to 0. Then 3x1 minus 3x2 is equal to 0. I want to eliminate x1, so I will add. When I add, this will go to 0, this will go to 0, so we get 0 is equal to 0. And whenever we find this, then we must think about infinitely many solutions. So this system has got infinitely many solutions, and if we want to get that, then you will let, for example, x2 to be equal to a given parameter t, where t is any real number. And for that case, then you come here and say x1 minus x2 minus t is equal to 0. So it means x1 is also equal to t. So x1 is t, x2 is also t. So it means for any value of t which is picked from a set of real numbers, for any value of t, then you will get x1, you will get x2. So that will be the required solution. And when we look at this, it means t can take up very many values. T can be 1, t can be 0, t can be 3, can be 4, can be any value. So for that case, it means you have infinitely many solutions, and that will be the answer. So we shall look at the next question. So you have 30 seconds to look at the answer, and please make sure you work within the given time. You are testing yourself about the concepts of linear algebra, so make sure you work within the given time. So the question is, if ax is equal to b does not have any solution, then the system is called. So that one, we should be able to get it. So you're having a system, you can have such a system. For example, you are having a system, this A represents a matrix coefficients, this B represents the constant coefficients, the constant values. So for that case, you can have a matrix, but such a matrix, so this is a matrix A, this is matrix representing x, then you are having the constants. So you have A1, A2, B1, B2, XY, B1, B2. So you're having such a system. So if such a system has got no solution, then we say that system is inconsistent. If it has at least one solution, then it will be consistent. So if ax equaling to b does not have any solution, then the system is called inconsistent. And that would be the answer. We look at the next question. So you have 30 seconds. So time is up. Let us look at the solution. We are told in Gauss-Jordan elimination method, we reduce the augmented matrix into, the answer is reduced echelon form. For echelon form is when you are looking at Gauss elimination method. So Gauss elimination method, you stop with the echelon form. Then reduced echelon form is when you are looking at Gauss-Jordan elimination method. So I think you note the difference. You stop at echelon form when you are simply looking at Gauss elimination method, but Gauss-Jordan, you have to make sure you reach at the reduced echelon form. So that will be the required answer. So you have 30 seconds to have that one answered. Okay, time is up. We look at the solution. If a system of two equations and two unknowns has no solution, then the graph looks like intersecting lines. That is when there is a solution. non-intersecting, here you have no solution. If you plot a graph, and you have lines like this, you draw your two lines and they are not meeting anywhere, they are parallel for that case, then you will say they are non-intersecting. And if they don't intersect anywhere, then there is no solution. Then same lines, if you draw and the line may be the two equations are giving you the same line, and then here it means there are infinitely many solutions. So for that case, it means our answer will be B, where we are having non-intersecting lines. So for a system of two linear equations in two unknowns, the solutions correspond at what we call the intersection points of their graphs. So for that case, if there is no solution, it means the lines are parallel, they have the same slope, but different y-intercepts, and thus they never intersect. So that is the answer for that case. We look at the next question. So you have 30 seconds to have that one answered. Which of the following is the linear equation in the variables x, y, and z? Okay, let us look at the solution. We are talking about a linear equation in the variables of x, y, and z. So a linear equation in these variables, the variables are supposed to have a power of 1, supposed to have the maximum power of 1. So this equation can be written as x minus 2y plus 0z, which is equal to 0. So it means here the powers for x, y, and z is 1. And for that case, this qualifies to be called a linear equation. For this case here, you are having a trig function. Any equations that involve trig ratios, involving logarithmic ratios, involving higher powers other than 1. For example, you can have x squared minus 2 equaling to 0. This is not a linear equation so long as the power of the variables exceeds 1 or is not 1. Even if it is a half, x to power half plus y is equal to 0. This is not linear, so the power for the variables must be 1. So all these ones here will give you non-linear equations. So this is non-linear. This is also non-linear equation. So it means our answer for this case will be A, where we have x minus 2y equaling to 0, because it can be written as x minus 2y plus 0z equaling to 0. So the powers for x, y, and z are all 1, and for that case, this qualifies to be the answer. So we shall have that answered. So you have 30 seconds. So let us look at the solution. We are told that which of the following is not a possible type of solution for a system of linear equations. So we have got 3 types. 1 is a unique solution. 2, we have infinitely many solutions. And 3, we have no solution. So exactly one solution means it is a unique solution, it is right. Infinitely many solutions and no solution. So exactly 2 solutions, we don't have this type of solution. So which of the following is not a possible type? So our answer will be D, because this is not a possible type of the solution, and that will be answered. So we look at the next question. So looking at the next question, so you have 30 seconds to get the answer. So we are looking at the first step in Gaussian elimination. 1, solving for variables directly. No. So it is rewriting the augmented matrix of the system of linear equations. This is true. Perform back substitution. This comes last. Identify the type of solution. No need. So the answer will be B. That is rewriting the augmented matrix of the system of linear equations. So next we look at the next question. So looking at the next question we are having, so you have 30 minutes to get 30 seconds to get that one answered as well. So let us look at the solution. We are given that what does it mean if during Gaussian elimination a row of all zeros except for the last entry is obtained. So we are given the system has a unique solution, the system has infinitely many solutions, system has no solution, and the system is overdetermined. So when we are looking at Gaussian elimination, we are transforming the augmented matrix AB into, we are transforming this augmented matrix into a row echelon form, But if you obtain a row of zeros, in this form, you have 0, all these are zeros, and the last entry is not a 0. For example, is C, where C is not equal to 0. If you transform this, for example, you had your matrix 1, 2, 3, 4, 5, 6, and other values here. Then you transform this into row echelon. So you realize you have 1, any value here. You have 0, 1, you have any value here. But this is the last entry. But you realize this is 1, maybe you have 2, you have a 3 there. So you realize that you are getting an entry where you have 0, 0, 0, but the last entry is 1. So when you have such a row where all these are zeros except the last entry, then it means that this system here has no solution, because 0 equaling to C, when C is not equal to 0, is impossible. You cannot have 0 equaling to 2. You cannot have 0 equaling to 5. This is impossible. So for that case, it means the system has no solution, and C will be the required answer, which means that our system is an inconsistent system and has got no solution. So that is the required answer there. So we shall look at the next question. So looking at the next question, so you have 30 seconds to think about the answer. So let us look at the answer. We are told that what do parallel lines represent in a system of two linear equations? So parallel lines, we have already looked at such when we were looking at the previous objectives. We said if you get parallel lines, this one means that there is no solution, because if there is solution, there must be intersection between the two lines. Either they are intersecting in the same line or they are intersecting at a given point. So this one, no. Infinitely many solution, that is not true. no solution will be the answer. So part C or C will be the answer. Now, no linear solutions, this is not right. So we shall have no solution if you get parallel lines, if you draw your given equations, using the graphical method. So for that case, it means this will give us no solution. So we shall have no solution for a system when you draw two lines and they are parallel. So there won't be any solution. So that is the required answer for that case, and we shall look at the next question. So looking at the next question, here is the question. And you have 30 seconds to have that one answered. So let us look at the required answer here. So we are told what distinguishes reduced row echelon form from row echelon form. So one, we are talking about the presence of leading ones. This is not true, though that one is one of the conditions that must be there. However, it is not what distinguishes the two. Then leading ones have zeros in every position above and below. This is true. The absence of any non-zero entries, this is not true, though it can be one of the conditions, but that can't be a guarantee. Then the requirement that all entries are 1, this is not true. So leading ones have zeros in every position above and below. That is what distinguishes. You can have 1, 2, 1, 0, 1, 0, 0, 0, 1. You can have such a matrix. You have another matrix, 1, 0, 0, 0, 1, 0, 0, 0, 0, or 0, 0, 1. So this is a reduced row echelon form, and this is row echelon form. So ones must be there. The leading ones must be there. However, this is row echelon, and this is reduced row echelon. So for reduced, where there is a leading one, in that column, all others must be zeros. If there is a leading one, all others must be zeros. If there is a leading one in that column, all others must be zeros. But for row echelon, even if you have a 1, it is not a must that these ones must be zeros. So that is what distinguishes them. So leading ones have zeros in every position above and below them. That is what distinguishes reduced row echelon form from row echelon form. And that will be answered as well. So we shall look at the next question. And this is the question. And you have 30 seconds to have that answered. So we look at the answer. So we are told what is a skew-symmetric matrix. So a skew-symmetric matrix is that matrix where the transpose is equal to the negative of that matrix. So a matrix where A transpose is equal to negative A is what we call a skew-symmetric. This is a symmetric matrix. If the transpose of the matrix is equal to the matrix itself, then we have what we call a symmetric matrix. But since we are interested in skew-symmetric matrix, then that will be part B. So let us look at the next question. And you have 30 seconds to answer that. As we have seen in the previous question, this should be easier for us now. What is a symmetric matrix? A matrix whose transpose is equal to the matrix. So that is A transpose is equal to A. That is a symmetric matrix. This is an asymmetric matrix. So no need for looking at this. So basically that is about a symmetric matrix. We look at the next question. So looking at the next question, we shall have, so you have 30 seconds to have that answered. So we are looking at what is a singular matrix. So by definition, a singular matrix is that matrix whose determinant is 0. So a matrix with diagonal elements, no. A matrix with a determinant 0, this is the answer. A matrix where all elements are 0. A square matrix with a non-zero determinant. So a singular matrix is that matrix whose determinant is equal to 0. And that will also be answered. So looking at the next question, we are told what is the term for a matrix with the same number of rows and columns. As we have seen, should be able to answer this one. So you should be able to get that one right within the 30 seconds. So basically a matrix with the same number of rows and columns is what we call a square matrix, not a symmetric, not diagonal, and not identity. So such a matrix is what we call a square matrix. So looking at the next question, if the determinant of a matrix is 0, what can be inferred about the matrix? So you have your 30 seconds to have that one answered. So this should now be easier for us. If the determinant of a matrix is 0, what can be inferred to this matrix? This matrix is singular, and at the same time, if it is singular, then it has no inverse. It is not invertible. If the determinant is 0, then the matrix is not invertible. It is not symmetric. It has infinite determinant. That is not true. So the answer is B. Next question. So next question, we are looking at a diagonal matrix. So this should be easier for you at the moment. We have looked at some of the related questions. So for a diagonal matrix, which of the following is true? All non-diagonal elements are 0. This is true. All non-diagonal elements are 0. All diagonal elements are equal. It must be invertible. It has no eigen. So basically, for a diagonal matrix, all non-diagonal elements must be 0. Or all of diagonal elements must be equal to 0. That is the most important point when you are looking at a diagonal matrix. So looking at the next question, we shall have, so you have your 30 seconds to look at that. So basically we are looking at the difference between Gaussian elimination and Gauss-Jordan elimination. So Gauss elimination ends at row echelon form. That is true. Then while Gauss-Jordan elimination continues to reduce to row echelon form. That is very true. So this is true. Gauss-Jordan elimination does not use Gaussian elimination is only for inconsistent, no. So Gauss-Jordan elimination eliminates row of zeros, no. So the answer will be A. And I hope you are having that one right. So please, as usual, make sure that if you haven't subscribed to this channel, please kindly do so. Hit in the subscribe button. It is completely free of charge. Don't forget to like, share this video to your friends. So let us move to the next question. So here we have the next question. What is the goal of back substitution in Gaussian elimination? So to find a row equivalent form of matrix, to determine whether a system has solutions, to solve for variables starting from the last equation, to transform the matrix into reduced row echelon form. So the answer here is back substitution is when you have like x plus y plus z is equal to 3. Then you have minus x minus y plus z is equal to maybe negative 2. Then lastly you have like z which is equal to negative 1. So you begin from this one here, you get y, you get x. So that is the back substitution in Gaussian elimination. So the most important thing here, or why we use Gaussian elimination using back substitution, is to basically solve for variables starting from the last equation. You start from here, you go to this one, you come to this. So that would be part C. So C will be our answer. So that is the basic goal for using back substitution. So we look at the next question. So the next question will be, so let us look at the next question. So the in Gaussian elimination, why is it important to use elementary row operations? We use elementary row operations to increase the number of rows in a matrix, no. To reduce the system to an equivalent, easier to solve system. This is true. To make all matrix entries 0, not necessarily. To graph the system, not necessarily. So our answer will be B. So we shall look at the next question, and please remember you have only 30 seconds to have it answered. So for a matrix that has 4 columns and 6 rows, what is the correct order? So 6 rows, 4 columns. So when we are writing the order of a matrix, we begin with rows and columns. So that is 6 by 4. 6 by 4. So 6 by 4 is C. So C will be the answer. When you are writing, you don't begin with columns. So don't say 4 by 6. This one will be wrong. So it has to be 6 by 4. So that would be the correct answer. So that is answered. So let us look at the next question. You have only 30 seconds to have that one answered. So we need to obtain the determinant of this matrix. So the matrix is A, which is given by 1, 2, 3, and 4. So we need the determinant of A. Determinant is same as multiplying the elements in this major diagonal, 1 times 4. Then you subtract 3 times 2. So this is same as 4 minus 6, and this is negative 2. So negative 2 is B, and that will be the required answer. So looking at the next question, so we need to obtain the trace of A. How do we get trace of a matrix? So trace of a matrix is obtained by adding the elements within the major diagonal. So the elements in this diagonal, we have 4 and 6. So this gives us 10. So trace of a matrix, trace of a square matrix, is same as the summation of entries within this main diagonal. So trace is same as 4 plus 6, which is 10. So your answer will be 10, and that is part A. We shall look at the next question. So we are asked the identity matrix IN is 1, a diagonal matrix with ones in the diagonal, 2, a matrix with all elements equal to 0, and 3, a square matrix with non-zero determinant, a matrix with the same rows and columns. Identity matrix is a diagonal matrix with ones on the diagonal. So a diagonal matrix is this matrix where you have our zeros of the main diagonal. But for it to qualify to be an identity matrix, these elements in the main diagonal must be equal to 1. So these elements must be equal to 1. But when you have such a matrix, this is a diagonal matrix. However, it is not an identity matrix. It is a diagonal matrix because elements of the main diagonal are equal to 0. So, but it does not qualify to be an identity matrix until this one is a 1. So when elements within this diagonal here are all equal to 1, and all others are zeros, then it becomes what we call an identity matrix. So let us look at the next question, and here is the next question. So next they are asking which matrix operation is not defined, addition of a 2 by 2 and a 2 by 2 matrix. So long as the order is the same, addition is possible. So this is true. multiplication of a 2 by 3 with a 3 by 2. This is possible since the number of columns here are equal to the number of rows here, so this is true. Addition of a 2 by 3 and a 3 by 2 matrix, this is not possible. It can only be possible if the order is the same. Addition is possible for matrices if the order is the same, so this is not true. Multiplication of a 3 by 3 with a 3 by 3, this is true. So the answer here, the one which is not defined, is addition of a 2 by 3 matrix and a 3 by 2 matrix, and that will also be answered. So we shall move on to the next question. That is, if A is equal to that, what is the determinant of 2A? So this is our question 44, and I hope you are following very well. So we are having the different options, and you have only 30 seconds to have that one answered. So here we need the determinant of 2A, and the determinant of 2A, let us first get 2A first. So 2A is 2 into 2, 3, 1, 4, and this is same as having 4, 6, multiply 2 into each of these, and what will be its determinant? What is the determinant of that 2A? That is same as the determinant of 4, 6, 2, and 8. So that is same as 4 times 8 minus 2 times 6. So this will give us 32 minus 12, and this will give us 20. So D will be the correct answer. So looking at the next question, let us solve the next question. So which of the following is a linear equation? At the moment, you should be knowing what a linear equation is, and for that case, it should be easy to see that this is not a linear equation, because you are multiplying x and y, though the powers are the same, but if you combine the two, it means xy has got the power of 2. So it means this multiplication here, it will not give us a linear equation. So this is not a linear equation. This one here, x, the power is 1, the power is 1, but e to power pi, this is a constant value. This is a constant value, so this can give us a linear equation. Because of this power half, this will be out, and because of this, remember, this can be written as y equaling to the square root of 3 times x to power half. We said the powers for x must be to power 1, so this will give us, this one will be true, though if this one maybe is x plus y, which is equal to e to power maybe something like that. Exponentials are also non-linear equations, so this one cannot be a linear equation. But since pi is a constant, e to power pi will give us a constant value, so this will be true. This cannot be right, this will also be not true, so it means B will be the answer. So having looked at this, we shall look at the next question. So we are given this, so let us try to look at the answer within the 30 seconds. A matrix is called a square matrix if the rows and columns are the same, meaning A will be the answer there. So looking at the next question, If A and B are matrices of order that respectively, then the order of AB is, you have 30 seconds. So let us look at that. We are told that A and B are of these given orders, 4 by 5. This is 5 by 7. Then what is the order of AB? When you are multiplying A and B, you realize the two matrices can be multiplied together, since this is 5 and 5. So it means these remaining values, the remaining values will form the order of AB. So 4 by 7 will be the order of AB. So 4 by 7 is this, and B will be our answer. So let us look at the next question. So the next question, the determinant of A, which is equal to that, is, so you are given these options here, and you have only 30 seconds to have it answered. So from here we need the determinant of A. And how do we get the determinant of matrix A? So first of all, we have the determinant of A as, we shall eliminate this and that. We take the determinant of 3, -2, -1 and 2, then -2 into, eliminate this and this, so you remain with 3, -1, 1 and 2, then -3 into, you eliminate this and this, you remain with 3, 3, 1 and -2. So this will give us, so get the determinant of this. This is 1 times, so that's why it remains the same. This will be 6 minus -2 times that is 2. Then -2 into, this is still 6. This is 6. Then minus -1. Then -3 into, next is -3 into, this is -6. -6 minus -6 minus 3. So when we try that, this is 4 minus 2 into 7. This is -3 into -9. So this will give us 4 minus 14 plus 27. This is -10 plus 27, and this will give us 17. So this will give us 17. So it means it is none of these. So that will be D, because the answer is 17. It is none of what is given here. So that will be the required answer in that case. So we shall look at the next question. So looking at the next question, we are given that. So you have the system of equations and you need to obtain the solution. And let us look at that in the 30 seconds. So looking at the solution, we are given the system, which system we need to solve simultaneously. So let us first multiply here by 2. 2x1 plus 2x2 is equal to 2. This will be 4. Then 2x1 plus x2 is equal to 2. So subtract. This will be 0. This will be 3x2 is equal to 0. So x2 is 0. If x2 is 0, then what will be x1? x1 plus 2 times 0 is equal to 1. So x1 is equal to 1. So we have 1 and 0. x1 and x2. So we have 1 and 0 as the answer. So that will be part D as the required answer. So from that we shall look at the next question. So this is so far question 50. So far we have 10 remaining questions. You should be evaluating how many answers you are getting right at the moment. And please don't forget to subscribe. Hit in that subscribe button before we come to the end of this video. Please make sure you have subscribed by the end of this video. Thank you. Let us look at the solution. A square matrix whose inverse exists is called a matrix which inverse exists is not singular. Yes, it is non-singular and it is invertible. So it means answer will be B and C. So that is D. So looking at the solution, we are told which of the following vectors is a linear combination of this. For two vectors, v1, v2, if v is to be a linear combination of v1 and v2, it means you should be able to express, to get scalars alpha into v1 plus maybe beta into v2, such that you are able to equate this one to v. In other words, when we get 1, 0, we add there as 0, 1, we should be able to get the v. V can be any of these. So we are looking at if you have 2 and 3. If you have 2 and 3, are you able to write any of these vectors here in terms of this? So for example, are you able to get alpha and beta such that you will be able to get that? So if you have alpha into 1, 0 plus beta into 0, 1, are you able to get that? For which values of alpha and which values of beta will you be in position to get that? So it means if your alpha is 2, for example, and your beta is 3, then you are able to write this. You are able to write this and this into a linear combination, and you get 2 and 3. In other words, when you get 2 into 1, 0 plus 3 into 0, 1, you'll be able to get 2 and 3. So 2, 3 can be written as a linear combination of the vectors v1 and v2. Likewise, if you have 1, 0, you have 0, 1, are you able to get the scalars alpha and beta such that this will give you 1, 1? For which value of alpha and beta should you put such that you are able to get 1, 1? If it can be written, if you are able to get alpha and beta such that you can equate it to 1, 1, then you will be able to give as a conclusion. But of course, this is true because if alpha is 1, beta is 1, you are able to get this plus this equaling to that. So this is very true. So in other words, for a linear combination, as we have seen here, alpha into v1 plus beta into v2 should be equal to v. And for our case, if our v1 is 1, 0, our v2 is 0, 1, and you need v, let us assume it is xy. So it means here you are having like alpha, this is 0, this is beta, which is equal to x and y. So for that case, you realize that alpha is equal to x and beta is equal to y. So what does that one imply? If your x is 2 and your y is 3, if for this case, if your v is this, then it means your x is 2, your y is 3. And for that matter, it means you are able to get alpha as 2 and you are able to get beta as 3. If your x is 1 and your y is 1, it means for this case, as we have seen, your alpha will be 1, your beta will also be 1. So it means you are able to write v1, v2 in terms of v, which v is representing 2, 3, is representing 1, 1. So next, when you look at -1 and 0, -1 and 0, so when we put it in the same, it means this is your x, this is y. So it means your alpha can be -1 and your beta will be 0. And for that case, you realize still you'll be in position to write this one here in terms of this. So we realize that all of them are satisfying. And for that case, it means the answer will be part D. So let us look at the next question. So next we look at this. We are given u and v. We need 2u minus 3v. So this is same as 2 into 2 negative 1 minus 3 into 3 and 4. So when you multiply this inside, this will be 4 minus 2 minus multiply 3 here, 9 and 12. So 4 minus 9 is negative 5. Negative 2 minus 12, that is minus 14. So it means our answer will be negative 5 and negative 14. And that will be A. So let us look at the next question. So here we are given u of x as that, v of x as this. All these are polynomials from polynomial of degree 2. This means this contains polynomials. This is a space of polynomials of degree 2. Space of polynomials of degree 2. So for that case, what will be u minus x? U minus x, or u minus v. U minus v, same as u is 3 x squared minus x. You are subtracting v, x squared plus 2x. So this will give us, subtract the corresponding values. So this corresponds to this, minus x squared, then minus x minus 2x. So this will give us 2x squared minus 3x. And that will be part, that will be part A, that will be part A. And that will be the required answer. So let us talk about the next question. So you have 30 seconds of that answered. So here we are looking at u and v being polynomials from a polynomial space of degree 1. This is a polynomial space of degree 1. So we are looking at u plus x. So we are looking u plus v. So we shall have u is 2 plus x. And we are adding there 1 minus x. So this will give us 3. This and this will give us 0. So that is 0x. So this is B. So this is B. This one is not correct because this is from P2, degrees 2. Here it is not indicating the coefficient of x. This is a constant. So from polynomial of degree 1, polynomial space of degree 1, then it means this would be the correct answer, and we shall have B as the correct answer. So next we'll look at the next question. So next we are given that question of these vectors here linearly independent. So we basically want to show whether these vectors are linearly independent or not. So we can test using the determinant method. You have v1 as 1 and 2, you have v2 as that. So we can obtain the determinant by having this as 1, 2, then this as 2 and 4. So get the determinant of this, and if the determinant is 0, then it means they are linearly independent, and if the determinant is not 0, then it means they are actually dependent. So for that case, let us look at the determinant of this. So what will be the determinant? That would be 4 minus, that would be 4 minus 4 minus 4. So 4 minus 4 is equal to 0. And if the determinant of the vectors, if the determinant of the vectors is not equal to 0, then it means the vectors are independent. If the determinant is equal to 0, then it means they are dependent. So for that case, we have two cases. If the determinant of that matrix is not equal to 0, the vectors are independent. The vectors are independent. If the determinant is equal to 0, the vectors are dependent. If the vectors are dependent. So for that case, this will imply that our vectors are actually dependent. They are not linearly independent. So the answer here is no. The answer here is no, because it is equal to 0, meaning they are dependent. But you can also test it by looking at v2 and v1. You realize v2 can be expressed as a scalar multiple of v1. So v2 is 2, 4. This is 2, 4, which is same as having 2 into 1, 2. So which means since this can be expressed in terms of the other, then the two vectors are linearly dependent. They are dependent. But you can also use a quick test, that is of using this one here of getting the determinant, and after getting the determinant, then you can tell whether it is dependent or independent. If the determinant is not equal to 0, then they are independent. If the determinant is equal to 0, they are dependent. So that is how you can easily tell whether the given vectors are independent or not. So that is done, and we look at the next question. So we have our next question here. So they are saying vectors v1, v2, and v3 are linear independent if they are linear independent if there exist scalars a, b, and c, not all 0. You have option B, C, and D. So try and see which one will give us the answer. So looking at the solution for this case, there exist scalars not all 0. If v1, v2, and v3 are linearly independent, then if you equate the linear combination, that is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, you equate this one to 0. If you equate this to 0, then alpha 1 must be equal to alpha 2 must be equal to alpha 3. And the only solution to this must be alpha 1, alpha 2, and alpha 3 all equaling to 0. If you have this, then it means the vectors v1, v2, and v3 are linearly independent. However, if one of these, if maybe alpha 1 is 0, but alpha 2 is 1, alpha 3 maybe is negative 2. If you solve this expression and you obtain this, it means the vectors v1, v2, and v3 are actually linearly dependent. So this is one of the other methods you use when you are testing for linearly independence or linear dependence. But you can also look at the quick method of using the determinant. You can use the determinant as we have seen in the previous example by looking at the determinant. If you get the determinant equal to 0, you should know what to conclude with. If the determinant is not equal to 0, you should know what to conclude with. So this is a quick test, but you can also use this as well, and you get the required answers. So we look at the next question, and for that case, only solution to this is equal to 0 is A is equal to B, which is equal to C. So your answer is part B. So here they are saying there exist colors A, B, and C, not all 0. We said if not all of them are 0, then it is linearly independent. If all of them, if A, B, and C are all 0, then we say V1, V2, and V3 are linearly independent. So your answer for that case will be part B. So looking at the next question we are having, so if V is equal to that, then V is a linear combination of So if V is equal to 3V1 minus 2V2, then V is a linear combination. It means V is a linear combination of V1 and V2. So we look at the next question. So which is not a vector space axiom? From the axioms of vector spaces, then this is there: associativity of vector addition, commutativity of vector addition, existence of additive inverse. Multiplying a vector by 0 always gives a vector 1. This is not true, so this is not an axiom of a vector space. So we shall look at next question. If U is any vector in a vector space V, what is U plus a 0 vector? So we do that in the next 30 seconds. So if U is any vector in a vector space V, then U plus a 0 vector will give you a U. So answer will be this. This is an additive inverse of U, and this is a 0 vector. So a vector plus a 0 vector will give us that vector. So answer will be B. So next we look at the next question. So we are given that V is equal to that. V is a set consisting of these vectors. V is from R3, which of the following is true? And the time starts now. So let us look at the solution. This is our last question. This is question 60. So this will be our last question. So it says given V is equal to that, where V is from R3, which of the following is true? We need to establish whether it is linearly independent, linearly dependent, whether it is both, or V spans R2. So for independence, we can use what we call the determinant. So we shall have 1, 0, negative 1, 2, 1, 0, then 3, 1, negative 1. So get the determinant of this, and from the determinant we can tell whether it is dependent or independent. So this is 1 into, so remove this and this, remain with 1, 0, 1, negative 1. Then minus 2, eliminate this and that, remain with 0, negative 1, 1, negative 1. Add there 3 into, eliminate this and this, get 0, 1, then negative 1, 0. Then try to get the determinant. So this is 1 into, this is negative 1 minus 0, which is negative 1, minus 2 into, this is 0 minus negative 1. Then this is 3 into, this is 0, this is 0 minus negative 1. So this will give us negative 1, this will be positive, this is minus 2, this is plus 3. So looking at this, you realize that we have negative 1 minus 2, negative 1 minus 2, that is negative 3, then plus 3, and this will give us a 0. So like the way we said, if the determinant of the vectors, is 0, then we should know what to conclude with. And if the determinant is not 0, we should know what to conclude with. So basically, since we have got the determinant, as 0, then it implies that, so this implies that since the determinant is 0, it means the vectors are actually dependent. It means the vectors are dependent. So for that case, our answer will be part B. So if the determinant is not 0, then they are independent, and that will be our answer. So that will mark to the end of our objective questions. Please don't forget to subscribe to this channel, or like and share this video to your friends who are preparing for their final examinations for linear algebra. And please don't forget to put the marks you have obtained out of 60 in the comment section. So please put how many you have obtained. So I'm waiting X out of 60 for how many you have obtained correctly out of 60. Please don't forget to put it in the comment section. So that's where we shall stop, and we shall meet in our next videos when basically we are revising more of the items for linear algebra. Please make sure you subscribe, like, and comment on this video. And thank you so much. We meet in our next session. Yeah.